Hello everyone, it's October 11th. All right, first of all, it's an easy question, so we're gonna not deal with this first. I want to talk about this method, the segment tree. So, as you guys all know, I am not the most proficient in segment tree, although I know it's a very, very important um, data structure. Segment tree, union find, right? Union find, I've dealt with a couple more times, and I'm a little bit more proficient in union find, but segment tree is still. And this segment tree is also different. If you take a look at the solution, this segment tree uses something called lazy. Okay, it's a segment tree with lazy tags. It's something never done before. So, and honestly, this explanation is not. I don't like it. Okay, I don't. It's kind of very specific to this problem. It's not generic. So I go for geeks, and they have a very good, I think, very good implementation of segment tree with lazy tags. And this implementation is basically following the geeks. So the basic idea is, before it goes to the basic idea of this, so in the past when I do segment tree, my way of doing it is actually different from what the official way is. Like previously, when I update a value, I will go in the tree node range, and then I'll go to the segment that contains my node and update there. And I will just keep updating up to the end. And when I query, it's the same thing, right? You have the query range and you have the actual range. And I will divide the tree node range into smaller and smaller to fit inside. And I will actually change the query range as I go, because every time I divide, I actually divide the query range as well. But this implementation is different. The query range, or when you update, these things don't never change. They stay the same. Okay. So what changes is your segment. The segment range changes. So if you want to update, we're talking about just generic segment tree. We update one value, right? You update one value, and you have your segment. And wait, how do the actually? I want to go back to the segment tree again. If you have one value, so this is not the lazy tag, it's just a generic segment tree. We can see the implementation, right? We can see the update. Let's go to the update, right? You have the tree. Oh, let's go to Python. You have the tree. You have the segment start, segment end, the node, the diff, and no, this is not node. What is I? It's the index of the element, right? And this is the node, right? And then we basically just take the node, take this is actually how the node is the place where you want to put into this range, right? The index of not index of the tree, but index in the actual range, and then you will update it. You see, I updated right here. It's already updated. That's updated the tree node. And after you update the tree node, you will go update the left and update the right. And when you do this, you don't change this, right? You don't change. You just keep the same one, and then you go to the left and you go right. So you update all the nodes that contains this range, right? So that's the update. It makes perfect sense. And when you query it, right, you have the query range. Now the query range doesn't change. You have your start and end for the segments for the seg range, and then you say if the seg range is contained within the query range, then you just take this value, right? You take it. Understandably, take it. If it's if the two range don't overlap, then you don't take anything. If they partially overlap, right? They kind of overlap, then you divide not the querying range, but the seg range you divide the seg range into 2, and it just recurs. So that is a much easier way to understand this problem than the way I was doing in the past, right? But this is different. This is not updating a single value. This is to update a range of values, right? Because we have this calendar, this events, right? So each event, when you add it to your seg tree, you want to update every value in this time range. Everything needs to be at 1, right? And then what you want is not a sum. You want the maximum. You want the maximum value over this range, right? Over a given range. So that's what we start with. And then this lazy tag idea is that because if you don't do lazy tag, every time you update, then you have to update like every single element you have to update, and that takes a lot of time. So you do the lazily, right? So you say, if I want to update this current range, right? We update a range, and you keep this range, the update range the same, and then you look for your seg range. And again, if your seg range is contained within the update range, then everything inside has to be updated. So there's just no question. You just update that node, and then we're done. If it's an outside, right, then we don't update anything. But we have to first check this laziness, right? The laziness is something in the past that has set up saying that, okay, this node needs to be updated because somebody previously has issued some update, but we lazily evaluate. We didn't really go down, but now we actually go down to that node, so we have to evaluate. So that's why we have to do this first. We evaluate whatever has been lazily put down for the current node, and then we update it. And then, since it's lazily, which means this value has not been acted on me, nor any of my children. So now I added to me, then I need to pass on this lazy evaluation down to my children if I have any. So this is very important, right? Very important. We just pass this on, but we don't visit them, right? We don't have to visit them. We just add to their laziness. And after we do that, you set it to 0. So that's that. And then it's just the same, right? If you're within the range, this is without the range. Is within the range, just add it, right? You just add whatever is, because everything in your range has to add this value. So you do this. And don't forget, because you're updated by this diff, you need to update the lazy because you're not visiting them, right? You're not visiting, so you have to update these as well. If they partially overlap, right, we just do the left and do the right. Right? We don't have to worry. We just do the left half, we'll do the right half. And once we're done, we get its value, right? We get its value, which is just in this left range, what is the maximum number of overlaps? And the right range, what is the maximum number of overlaps? Now we say, what is the maximum number of overlaps of me? That has to be the maximum of the left and maximum of the right. But very importantly, it has to also be this, because I have implemented this. I added some lazy, so maybe I'll be bigger. Who knows? Nobody knows. So we're gonna have to do this as well. So all three, we get a maximum, and that's it, right? That's it. So this one guarantees every node, right? We have a tree, we have a lazy. Every node's value is the maximum overlaps in the range represented by the node. And every time we update, this tree will get updated. And then the question we want to ask is, what is the maximum number of overlap overall over the entire range? So that's why when we want to book, we update it and then we return this. This is the root of the tree, right? The root of the tree corresponds to the largest number of overlaps across the entire range, which is from 0 to this value. Now, one tricky thing to keep in mind is when we do the segment tree, we always want to have the start and end to be closed. It's a closed interval, right? Because we like to do this. We want to set this to mid and this to mid plus 1. So it has to be a closed interval. It cannot be open. But the question is actually open, right? The left is closed, the right is open. But we say we don't want that. We want both to be closed, so there will be less ambiguity. And then everything like can be smaller equal to, that this everything will be nice and easy. And just the only thing is when we do this, we'll have to call n-1. Yeah, so that is the implementation from Geeks and Geeks for segment tree with lazy propagation. That's what they call it, a lazy tag, whatever you call it. It's a lazy propagation. And my thing is completely derived from this. If you see here, this is update, right? Lazy is not equal to 0, we plus, but here, this is to compute a sum. So it has to add everything up. So whatever the lazy is has to apply for every single element. So you have to do this. But in my case, it's not. We're not adding up everything. We're trying, like the whole range will add 1. Like everything just add 1. We don't want the sum. So because of that, I only just add this. I don't have to add that. And then you see we here, and then we put the lazy. We put the lazy here, right? And this is out of bound. This is inside bound. We do the same. We do the diff. But again, here we just do one diff, and this we do more diff. And then we do this, exactly the same, right? Exactly the same. And then we have this mid, and again, this is plus, but for us, it's not. It's finding the maximum among them. And that's it, right? That's the, and to get sum, it's the same thing. Well, to query this range, you have to check the lazy as well. So you have to check the lazy. And then the reason we don't have to check the lazy here is because lazy 0 will always be 0, right? Nobody will put things on the root. So the root will never have lazy. So we just query this and we're good. But if we're querying some range, you have to first check if this node has some lazy. If it has some lazy, you have to apply it, right? And remember, every time you apply, you have to propagate it to your children. And then it's just the same thing, right? It's just the same thing. If the segment is inside your range, you return it. If it's outside the range, you do the left to the right. And in our case, if we want to query a specific range, then this would just be a maximum of the left, a maximum of the right, something like that. But honestly, I don't really think so. There's actually, I don't know, in our case, the left and right, we're querying them, we might have to update this one as well if we really want to. But anyway, so this is that. And the time complexity is only O(n). O(n). Well, I think it's O(n) because we have lazy. We evaluate lazily. So every node actually gets evaluated once. That's how I think, but I'm not 100% sure on that. Actually, for this one, they don't say it's O(n). I think their time complexity is O(n) log C. Yes. Yes. It's talking about this, yeah. Okay, so we have one more to go through today, which is balanced tree. We will take a look at this, but now we can go back to here. I might take a look at this later instead of doing it right now. Anyway, largest perimeter triangle. Give an integer array, return the largest perimeter of a triangle with a non-zero area formed from 3 of these lengths. If it is impossible, return 0. Hold a second. Number, okay, we can be longer than 3, okay? The largest perimeter of a triangle with a non-zero area. So we want to find 3 values. I want to find the largest of them with a non-zero area. And it has to be a triangle, so the sum of 2 must be larger than the third. So we can sort it, okay? We look for the last 3, right? And we see the sum of the smallest 2 if it's larger than the largest one. If it is, then that's the answer. If it is not, if the sum of these smaller, sum of the smaller is not larger than the largest, okay? If the sum of the smaller is not larger than the largest, then what? Then sum of any of the smaller won't be larger than the largest. So we pop the largest and then try it again. Yeah, that's how I'm going to solve it. Let's try this. Oof. I have to do yesterday's. All right. So I think we're going to sort it first. And then we are going to say, we'll keep going until we say while len nums is larger than 2. Okay. We say if nums minus 3 plus nums minus 2 is larger than nums minus 1, then we return I just add them together, which is fine. Alright, we just add this together. Otherwise, nums.pop. And we return false. Yeah, this is actually an interesting problem. Yeah, it is easy, but it's fun. And in fact, it is possible to generate lots and lots of test cases for this, so I'm not worried. It'll be fun. Nums largest. Alright, let's generate some test cases. Alright, so random port randint, right? 10 test cases, I want to print. Okay, for this in range, let's go 10. Randint. Yeah, we can do more. I don't know. This will be fun. Wait, hold on. What the hell? Oh, range. That'll be fun. Actually, I don't think that's the good way to run the test cases, so I am going to make a smaller. It'll be more fun this way. Okay, let's try this. Oh, what's a new problem? Oh! Oh! Why do you return? I was like, what the hell? I think for the past 4 days, right? Never got it right on the first try. I mean, today was just, dear Lord. Didn't notice it. Didn't notice it. Why you return false? I don't know. Maybe there are even better way to solve this. So let's see. Sort nums and then try the largest 3 values if they can form a triangle. We're done. Otherwise, pop the largest and try again. Log in, we have sort. Okay, let's see what type of solution we're talking about. Sorting. Yeah. This is considered like, what should I say, common sense, right? All right, I don't want to do this right now. Let's try to, I think one of the problems has been staying here for a while. Let's try this one. Number of ways where a square of number is equal to product of 2 numbers. Given 2 arrays of integers, nums1, num2, the number of triplets formed under the following rules. Triplet type 1. Num1, num2, where 0 and, okay, so not equal, cannot take the same value. Type 2, nums2 equals num1. So number of ways where square of numbers is equal to product of 2 numbers. Okay, so first one, 4 times 4, right? Type 1, 1, 1, 2. Oh, all triplets are valid. Okay. $1,000. 1,000. O(n) squared is allowed. Yeah, O(n) squared. You wanna try O(n) squared? Maybe. And this is, yeah, we just multiplied everything and then see if it's inside here. I have to counter it, right? So we counter nums1, and this we basically multiplied all 2's together, and we counter that one as well, because each one will be different. And then for each of this value, we check this value, and then we multiply the 2. Let's try it. Maybe, I mean, 1,000, if it's lenient enough, it's possible. I think we'll be able to pass. But if they are not lenient, then we have trouble. Let's see if they're lenient. So I want, what do I want? I want counter. Okay, so we're gonna say n1 counter equals counter nums1. We need an n2 counter, which is counter nums2. We also need n1 molt. Let's call it n1c, n2c. n1 molt c. This is gonna be a counter. and n2 mod c. That's going to be a counter as well. Okay, so basically we're going to do it. I think we can. Why don't we write a function, right? Why don't we write a function? Def as a helper. Let's do A and B. Okay. B. That's what we're return integer. All right. Okay. AC equals counter A. Okay. And we can say B mod C. BMC. BMC is a counter. Okay. For I in range len B. For j in range I plus 1 to len B. BMC BI times BJ, right, plus equal 1. And for key value in AC dot items. When I have a res equals 0, we say res plus equal to v, the number of different on A, times bmc dot get. Actually, no, don't mean to get. We just to k. Right, the key. And the return. We can actually just return sum. Right, v times bmc k. Something like that. Okay. Then we can say return helper nums1 nums2 plus helper nums2 nums1. Okay, let's check if this works. This 1. This will be 9. And this will be 2. Okay. Nums1, nums2. Num triplets. All right, the first one is not right. That is interesting. I can print. Let's print AC, print BMC. Just for the first one. Okay, so we have 7, 4. Oh! Squared. Damn. For V in A, V times V. My bad. Forgot. Squared. Syntax error. Yep. Okay. I don't know, but we can run some larger values and see if it works. Okay, let's run some values, some serious values. To list. Okay, for 10 tests as usual. Print 1000. Okay, print rand int 1, 10 to the 5th, for this in range randint 1000, 1 to 1000. Okay, that's the first one. Can we copy this? Yes, we can. That's the same thing, huh? Okay, let's do this. Holy crap. I was worried. That'd be too many numbers. Let's see if it breaks. It might break because 10 to the 5th you wanted. Yeah. Might not. We'll see. Let's try it. It definitely works, but it's O(n) squared. Okay. O(n) squared works. So then the question is, can you optimize it? Can you optimize it? Well, this is naive O(n) squared solution. It works because the length of input nums1 and nums2 are not longer than 1000. Okay. Okay, now the question is it possible to make it better? Well, for one thing, I mean, we can counter it first. Yeah, we can counter. Actually, we don't have to do this. We can just counter this, right? And then, if we can, I want to say for kv, right? BMC, k times k. Right, maybe we can avoid, yeah, but we're still doing this. It's the same. It's the same. This doesn't really make it any better. But division? I don't think division is the way to go. What else can you surmise? I mean, we can obtain all this, right? The square of all this. And then we go in here. That's O(n), and we divide the first one. For each one, for each one, O(n). For each one, we divide on this, and we binary search. I honestly don't think it's gonna be any better. Because we have a bunch of this. For everything, we have to go at least half the length, right? So all this times all this. And then plus all this times all this. So mn, 2mn. What is this? This is O. Maybe it's actually faster. Hold on. This is OM squared plus ON squared. Yeah, ON squared, ON squared. The other one is going to be OM n log m and OMN log n. So MM times log. You want to try? Yeah, we can try. It might work. But we have to do division. Ah, we don't have to do division. I see. Same thing with helper. Yeah, we have to do helper. So we're going to do the same thing. In fact, we are going to do this one as well. I'm actually gonna we're actually gonna say times v for v and a, something like that. And then for each of them, now b dot sort. Ooh, let's sort them before. Yeah, we sort them. Oh, O n, that's O n log n. Huh. Anyway, so we don't have the sort here, right? We don't have the sort here. Then what? Then we just go through everything. We divide, right? If it's too small, then if the value is outside, then we just move on to the next one. We divide. And first, we try to find, then a second, try to find, and if any time, because it has to be a small times a big, right? If any time the result is smaller than we'll call it, and if it divides something small, already smaller, so like if these things are too big, then yeah, there's nothing. And if it's something, if it does not exist, okay, let's try it. So we say for key value in ac.items, okay, and qr equals div mod k. Oh, should I get rest equal to 0, right? So for b in b. How about this? I want to call it count. Let's say call AA, right? For b in b. AA of bb, right? If r is equal to 0, okay? If r is equal to 0, which means this one can divide b, then we need to say, oh, we need to go from bisect right. Okay, index equals to bisect right. We're gonna go b, and we search for q, right? Oh, hold on. If q is smaller than bb, right? So a divided by this is something smaller, then we will break. No need to keep going. Otherwise, we do this, and then we say if b index minus 1 is equal to q. Right, if b is equal to q, then res plus equal to count. Okay, so we found something. And return res. I do the same thing. Oh, try it. Oof. The heck? $12. That is bonkers. How? We have to counter the b as well. Seriously, we have to counter the b. Yeah, I have to counter the b. Why don't we counter them outside? Yeah, I'm thinking. we can counter both outside, right? N1C yeah, so the problem is we want this list to be unique, right? And then we'll find multiple, then that's how we do it. Right, so we have N1, we have N2 counter, and we have N1 unique sorted. N1 unique, we can say sorted, N1C, N2 unique sorted, N2C. Then we just call AC, BC, A unique, B unique, right? Then we don't do this. Then we start from AC dot items. You can say A, right? And in fact, do we need BC? B, yeah, we do need. So now we say for B, A count, okay? A count, B count, BC dot items. Man, that's also OMN. Okay, so we have A plus B, then div mod A times A on B, right? And actually, A doesn't matter, B actually does matter, so I cannot do this one. I have to go B in for B and B unique. We don't need A unique. We don't need A unique. Just need B unique. Okay, and now we try this, and now we say if Q is smaller than B, then that's it. Otherwise, if this index will be B unique to Q, and if B unique, this is equal to Q, then rest plus equal to A count, right? This is how many that can make into that, multiplied by what? Well, we have the B count, right? The B count, we have B unique, we have the Q. So, are you saying BC B times BC Q? And we'll do helper N1 count, right? And then N2C, then N2 unique. And this one will be reverse, N2 count, N1 count, N1 unique. Try this. Oh my god, it's even worse. That ain't right. Hold on, let me think again. Oh yeah, what you're gonna do when it's the same value? Holy crap. I see. If this is equal to Q, right? It depends. Okay, so A count is fine, so this one we have to handle it. So if B is not equal to Q, if B is equal to Q, then will be BC, then B is the same thing, this times BC B minus 1 divided by 2. Yep. Let's try the others. I honestly I don't think this will be any faster. No. What do you think the runtime? Might be faster. Okay, we have O n plus m. M equals line num1, nums1, n equals line nums2. Okay, so let's go m plus n plus m log m plus n log n plus m n log n plus nm log m. So equal to om plus, well, these thing dominates, right? So these dominates this. So we'll go this. And this dominates this. So I'll go mn log m plus log n. I don't know. This is m squared plus n squared. M times m. It depends. If you have, I don't know. Well, before we do anything, we have to first make sure this one works as well. We have a large test case that we can try. Oh, it seems to be faster. Huh? Oh, it's much faster. Well, it's faster, I think, is because we have the early break, so we don't have to go through everything. And now we have binary search. That's also make things faster. Yeah, I guess that's that. TwoSum OMN. That's almost OMN. Oh, why you just forgot about TwoSum? No. How do you do TwoSum? Oh, you do TwoSum. Man, come on. You're dumb. Yeah, you're dumb, man. Why you do that? Why you do that? I always think about binary search. You don't have to do binary search. There's no need. Holy crap. Alright. Let's rewrite this. We have the count. You put the count in yourself. If r equals to 0 and q in BC, I don't understand. Then this will be this. Yeah. So no need to binary search. Yes, it is. No need to binary search. TwoSum is sufficient. Especially we already have. We prepared everything. I don't know, man. I don't understand. What the hell is going on in your head? Right? Like what the heck? It doesn't make any sense. Like seriously, it does not make any sense. Alright. Oh no, my test cases. Come on. It's like, man, dude, what the hell are you thinking about? I don't know. I don't know. Like, whenever there's two sum, my first idea is always binary search, binary search, binary search. You don't have to. You already get the counter. You already get it. Jeez, man. Come on. But yeah, this is like we guessed, and this is, yeah, we do binary search. We don't need binary search. All right, I like this problem. I hope the interview will be like this. All right, I'll see you guys tomorrow. Adios.